This call is now being recorded.
Okay. So in the last class, slideshow. In the last class, we discussed what is crypto function and its application, as well as non-crypto functions and its application. And also we discussed few non-cryptographic hash function where they are not at all secure, right? And rsync, R synchronization command where this non-cryptographic hash is used. That is also we discussed. And cyclic redundancy check, why it is used, that is also we discussed in the last class. So we shall move to the next topic, where we are going to study very popular crypto hashes which were used uh, in initial days. That means this MD5 and SHA1, those are the widely used hash functions to encrypt the messages. Okay. So as I said, MD stands for Message Digest File, right? And one second. Just wait for a second. 1 second. Okay, sorry. Let's start. This MD stands for Message Digest 5. Okay, and this is a successor of Message Digest 4, which in turn was the successor of Message Digest 2. And as you can see here, it was invented by the guru of crypto, that is Ron Rivers. Fine. The output of this Message Digest 5 is 128-bit output, and as you can see here, this Message Digest 5 where the collision were found. So what does it mean? So it is broken. When it is broken, it was no more in use. Okay, and one more hash function which is used was secure hash function. See, there are many hash functions that were in use, wherein here I'm listed only these two because these are very widely used secure hash function initially. Okay, that's why I've listed these two, and these two are given in your syllabus as well. SHA stands for Secure Hash Function 1, where it was used in US government for a what? Okay. You can see here the output of MD5 is 128-bit, whereas here it is 160-bit output. And the hash function which the function which is used in MD5 and MSHA, where hash is performed on the message, where messages are represented in the form of blocks. Okay. So as time passed, even SHA was also no more secure because collision were found in this algorithm as well. Fine. So we moved on to the next secure hash function, which I'll be discussing in the next slide. Okay. Before that, I want to discuss about this avalanche effect. So what is this avalanche effect? You can see at the background this flow of the snow, right? So you can see on the peak where if there is a small change in the climate, or if there is a wind in the climate, where if a peak is surrounded by the snow, then if there is a small changes, you can see the flow of the snow like this very fast, isn't it, right? So as it moves down, the size of the snow flow will increase, right? In the same way, whatever hash function that I'm going to discuss in the next slide and follows avalanche effect. Okay, that means number of you can see here if there is a change in one bit of input, the output bit will also change. That means the hash function that I'm going to discuss will consist of many rounds. Okay, so in each and every round, you can find the changes. If one bit of input changes, then in each and every round, the changes you can find it. So the changes will cascade to the further round. Okay, that is what the avalanche effect. So if this method or this design is followed, you can see the hash function is more secure. Okay, so this is similar to the design of block cipher. That is what it says. Let's move on to the hash function. The name is tiger hash. Since MD5 and SHA1 were found with collision, it was no more used. That's why the new hash function is designed that named it as tiger. Why it is named it as tiger hash function? Because it is very strong and fast. You can see the tiger, it runs very fast, right? Not though as cheetah, but it runs fast and it want to hunt, right? So that's why this hash function is compared to the tiger and named it as tiger hash function. As I said, it is fast and strong. So tiger also it's a strong animal, isn't it? So whatever hash function here I'm saying the tiger hash function is very strong because it's very difficult or no collision found in this hash function. That's why we say it as a fast and strong hash function, right? And this hash function is designed by Ross Anderson and Ellie Beham. So those are the leading cryptographers. So the criteria of this hash function is it is more secure compared to MD5 and SHA1, and this is optimized for particularly the processor which is of 64-bit. Okay, the MD5 and SHA1 were not compatible with 64-bit processor. That's why the new hash function is designed and it is optimized for this 64-bit processor. And you can see it is an easy replacement for MD5 or SHA1. As we found collision in these two algorithms, the tiger hash function were in use. And in this tiger hash function, there are many series as well. Tiger hash function 1, tiger hash function 2, 6. The series are also available with slight modification to each other. Okay. So this is the outline of hash function. Okay. Let me take a highlighter. Okay. This tiger hash, one second. This tiger hash function, it represented with the help of this diagram where you can see the input is divided as message blocks. Here I'm representing it with 3 blocks, right? So the message is divided as 3 blocks. This is fed as input for the hash function. Once this hash function is applied, you will be ended with hash value. Okay, you can see here this MD5 or SHA1 where input is divided as 512-bit blocks. If it is input is not can't be divided as 512-bit blocks, we will be padding it with 0 or 1 or X. It depends. Okay. So whereas in this tiger hash function, the output is 192 bits. See here I said 3 blocks. The input is divided as 3 message blocks, right? So each message block will be of 64 bits. Okay, output will be 192 bits for this hash function. Okay, so this is actually outline of this hash function. We'll see in detail in the next slide. So this hash function follows many number of rounds and all is of 192 bits. This hash function consists of 4x boxes, okay, wherein each box maps 8 bits to 64 bits, okay. And here for this hash function, a key schedule is also used. So this is the outline of this hash function, where you can see the input is divided as 3 blocks and the output will be of 192 bits, and each 192 bit is divided as 364-bit words. It consists of many rounds and each round will be of 192 bits output, and it has 4S boxes. We'll see what is 4X boxes for the slide, where each maps 8 bits to 64 bits. Okay, and also key schedule is also used. This key schedule is nothing but a computation. We'll see at the end of this topic. Okay, am I clear to everyone till here? Yes. Am I clear? Have you all understood what I explained till now?
Yes, ma'am.
Yes. Yes, ma'am. Okay, fine. We'll see. Excuse me. The complete working of this Tiger hash function. Okay. So as you can see in this figure. Okay. So here, this figure represents the outer round. Okay. And also you have inner rounds, and also you have the S boxes here. That means it's a calculation part and the key schedule. So here we are going to discuss 4 important topics with respect to Tiger hash. I mean, each hash function, with respect to Tiger hash function, all these 4 steps are followed. What is it? The outer round calculation, inner round calculation, and S box calculation, and the Tiger hash key schedule. Okay, we'll see one by one now. So these are all the computations involved. Okay, in each and every function, it consists of, it's going to perform the calculation so that the finding collision should be difficult for the intruder or to an attacker. Okay, let's consider this input be X. Okay, so let's treat input as X. You can see here. Okay, X is padded. If required, the input is padded. Why? Because so each input should be of how many bits here? It should be of 512 bits. So X, I'll treat it as from X0 to Xn minus 1, where each Xi is of 512 bits. Okay, so this is input. Okay, out of this series, one is selected, and this will be of 512 bits. This input is given to W. We'll see what W in the next slide. Okay, so this X is divided as 3 blocks. You can say that is A, B, C. Okay, so initially these are the constants that is considered here. Okay, and this ABC is of 64 bits. Do remember, it should be of 64 bits. Why? Because the output what we get it with respect to Tiger hash function should be of, the previous slide I've said, it should be of 192 bits. That's why this input is treated as 64 bits each. Okay, and this will be represented in the form of hexadecimal. Okay, so compared to MD5 and SHA1, it is treated as more complex complicated by why? Because for the attacker, it should be difficult to break it. He is not supposed to find any collision to break this function. That's why each input ABC will be of 64 bits and it is in the form of hexadecimal. Okay, I hope this is clear to everyone. You can see here this 64-bit input is fed as input for this function f5. We'll see what this f5 in the next slide. Okay, so there will be n iteration as you can see in this diagram. So this initially ABC is treated as constant and the output of this outer round calculation will be in the form of ABC itself and it is of 192 bits. I hope I'm clear to everyone. See here you can see this is fed as input for F5 and output of this function for F5 function I'm feeding ABC as well as this W. We'll see what is W in the next slide. There are also some calculation is involved. Okay, this is fed as input for F5. This fed as input for F5. After computing, okay, whatever output that I get it from this function is also treated as ABC, but this ABC is fed in the combination. You can see here, if I treat this as A, okay, this as A, this as B, and this as C, then you can see here, C is fed as first input, then A, and then B, okay. This changes has been made here. This fed as input for F7, okay. This output of W is treated as key schedule. This key schedule we'll see in the next slide. Now, as of now, you assume some value is fed. Okay, the output of this will be treated as W again, and again it is fed as input for this F7. So this function has input, which is the output of F5 and W, the input to this F7. Again, the output of F7 is treated as ABC, and this is fed as the input for F9, where B is first, C is next, and A is last. For this also, the W is fed as input. After performing calculation, you can see at the end what operation has been done. XOR, minus, and plus. On what output of this will be represented as ABC itself. Okay. Here the input fed as also ABC. The output of final round is also ABC. Now, such outer round calculation will be done for 3 times. To remember, the outer round computation for tiger hash function will be of 3 rounds. Okay. As I said, the next part is inner round. See, this is one outer round, okay, for which here, F5 I said, right? This here, whatever calculation is done, that we call it as inner round. So this, this F5, so whatever F5, F7, F9, this will be represented as inner function. Okay, as you can see here, each FM consists of 8 rounds. So this we call it as inner round. Whatever we discussed here, outer rounds, okay, now we are looking into the inner rounds. So this calculation will be performed for 8 rounds. Do remember this. This topic is very important. So here, as you can see here, W is represented as the 0 to n. 0 to n minus 1, that is W7. W0 to W7. So it consists of 8 rounds, right? That's why capital W is equal to the smaller W0, W1, W2 till Wn minus 1, that is W7. Here it is given. Okay. And here the W in total, you can say it is of 512-bit input that is fed to the function Fm. Here you can see this W is of 512-bit. This is fed as input to this F5 And whatever the computation that happens here, that is represented in this diagram. That we call it as inner round. I hope this is clear to everyone. Okay. And whatever output that we get it here, here everywhere, that is will be of 64 bits. Okay. And this fm comma 0, that means fm comma I, fm comma 1 or fm comma 2, this value depends on X boxes. We'll see what is X box here. Okay. So here fm comma 0, right? So what is me here? The input A, B, C. Those are the inputs from the previous round. You can see in the initially we are feeding here ABC, right? And here the output of this is treated as ABC. That is fed as input to the next part of the calculation. So that's why input values of ABC, that is considered from the previous round. Okay. And whatever WI am feeding here, that will be of 64-bit block of 512-bit W. So capital W consists of W0 to W7, right? So here each WI will be of 64-bit. And subscript M, that is here, this M, that is a multiplier. And whatever C I'm considered in the previous slide, it takes the series from 0 to 7, that is C0 to C7. Okay. So the output of this fm comma 0 is represented with the help of this calculation. I mean, output of fm comma I is, that is, here you can see output is A, B, C, right? So how C is calculated? C XOR WI. For each round, you should calculate this. A is equal to A minus S0 of C0 XOR S1 of C2 XOR S2 of C4 XOR S3 of C6. In this way, the calculation is performed and output will be considered as ABC. Okay. So here, what is this S, right? This Si, we call it as S box in Tiger hash function, where each 8 bits map to 64 bits. Okay. But it is considered for the calculation part. Fine. So whatever I discussed here, this, as you can see, it involves many rounds, right? So why these rounds are considered? So that attacker should not be able to break this hash function. If so many calculations are involved, it's difficult for the attacker to find out each and every round calculation, right? So that's why we treat it as this hash function as very secure. And now the question is, what is key schedule, right? So in the initial in the outer round, you can see the key schedule is also included for the calculation, right? In the outer round part. So what is this key schedule? Here you can see the calculation part. What is W0? I'm feeding here W0, W1, W2, right? In the inner round calculation, that W calculation is represented in this picture. You can see W0 is equal to W0 minus W7 XOR on hexa value. See, this is the standard value that they'll consider for the XOR function. In this way, all this calculation is made and fed as input to the respective rounds. Okay. So, if any small change in the input, capital X is input here, right? That is divided as ABC in the first outer round. So, if there is a small change in X, it will produce large change in key schedule output. You should remember this. If there is a small change, the output of key schedule will also changes. So, this we call it as avalanche effect. Okay. So, let's summarize this hash function, Tiger hash function. As I said, Tiger hash consists of 24 rounds in total. That means 3 outer round calculation, which is that this one. 3 outer round calculation, and each outer round will be of 8 inner round calculation. Okay, so that means 3 into 8, how much? 24. In total, it consists of 24 rounds. Next, whatever intermediate value or the hash value that we obtain from each round, that will be of 192 bits. The next is, you can summarize generally as it consists of S boxes, okay, and also it consists of key schedule where small change in message affects many bits in the intermediate hash value, and multiply where S box are involved, okay. And as I said, this ensures the strong avalanche effect, okay. So that is about the hash function or Tiger hash function. And at the end, you can conclude that the Tiger employs the confusion and the diffusion. In the first module, we discussed the basic design principles with respect to any crypto algorithm. It should consist of confusion and diffusion, right? What is confusion? Obscure the relationship between the plain text and the ciphertext should not be known to the attacker, right? And also diffusion. What is diffusion? Whatever the letters that is present in the plain text should spread over to the ciphertext. So it should not be, attacker should not be able to find out the plain text even though he receives ciphertext, right? So that where this Tiger hash function satisfies both the design principle of crypto algorithm. So you can conclude that the Tiger hash function is more secure compared to message digest 5 or secure hash function 1, which we discussed in the first slide of this in this class. Okay, is this clear to everyone? Tiger hash function? Yes. Let me know. I'm audible, right? Anyone? Okay, Tiger 1, could you please repeat it? Yes. So this one, Tiger 1 round. See, this actually the computation starts from outer round. Okay, this calculation happens in 3 rounds. Okay, each outer round consists of 8 inner round calculation. This is the outer round, as I said. This xi is nothing but ABC. xi is divided as ABC. Okay, and this xi is of 512 bits. If xi is not 512 bits, it is padded to make it as 512 bits. Okay, this fed as input to this hash function, where along with the w. Okay, w as we discussed in the last slide of this topic. Okay, this xi is divided as 3 blocks A, B, C. Okay, and this will be in the form of 64 bits. So in total, at the end, you have to get 192 bits. So 64 bits, A is 64, B is 64, and C is 64. This fed as input for this F5 function. F5 is nothing but what? This here, the inner round computation will be done. Okay, that to perform this computation, W is fed as input along with ABC. The output of this outer round is fed as input for this F7, where again W is fed as input, output of FI is fed as input along with the key schedule. Okay, and again after performing all the calculation, at the end you will get ABC, which is also of 192 bits, where A is 64 bits, B is 64 bits, and C is 64 bits. Now the question is, what calculation is done at each function? So that calculation is represented in this diagram that we call it as inner round calculation. Okay, as you can see here, W is set as input for this Fi, right? This Fi is nothing but this whole diagram. This whole calculation will be done at this function Fi. Again, the same is done at this. Again, the same calculation is done at this with different inputs. Why? Because the output of each function will be different, right? That's why. Is it clear, Shreya? Yes? You can unmute your mic and ask me. Understood? Okay. Yeah, fine. So, as I said, it follows the design principle, that is confusion and diffusion. Fine? Okay. Next topic, that is hash map. We'll see in the next class. That's all for today. Okay. And please drop your USN and name in the chat box. If any doubts, let me know. Please drop your name and USN in chat box. That's okay, Shreya. I hope I cleared your doubt. You can drop me a message in chat box. Okay, Shreya. Those who have entered your USN and name can leave the class. Thank you all. Prithvi.